Hi folks, we're going to take a look at page 158, number 21. So here they've got an offshore well is located 5 kilometers from the nearest point along the shore, which they call A. All right, so let's do that here. Say this is the shore. Somewhere out here we have an oil well, and it's 5 kilometers from the nearest point, A. Okay, so start the drawing. It says a pipeline is to be built to take the oil from P to a refinery that is 20 kilometers along the straight shoreline from A. All right, so again, we'll assume straight shoreline here, and we'll say that's the refinery, and this is 20 kilometers away. All right, and then they tell us that it costs $100,000 to lay pipe underwater, but $75,000 on land. And they want to know what route we should take in building this pipeline so that it costs the least amount of money. All right, so let's take a look at the possibilities. So ideally, you want to maximize the amount of land pipeline because it costs less, and minimize the amount of water pipeline. So the way to do that would be to go straight across and then to the refinery. The problem with that is that it's going to be the longest route. All right. So the other way to think about it is, well, let's just make it the shortest pipeline possible. So that would mean going straight across underwater. But of course, the problem there is that you're building all along the route, which would be more expensive. Okay, it could very well be that one of these is the best route to take, but it's also possible, and this is what you always want to do when you draw a diagram, is draw the most general situation, is that you've got a portion of the pipeline that's going along the water, and then another portion that's going along the land. Okay, and it's some combination of the two. Now, notice here, I think I'm going to assume that we're not going to go sort of backwards and then down. It seems pretty clear that that would cost more money. Now, having said that, there might be some reasons why you would have to build it that way. Perhaps the water's too deep in this area here. Perhaps there's a school of man-eating sharks with laser beam eyes, and so you have to build it in some other way. Okay, but we're going to assume here that they haven't given us any of these restrictions. All right. So essentially, what I have to do is determine an expression for this length and multiply it by 100,000, because 100,000 per kilometer, and then an expression for this length and multiply it by 75,000, and then add those two together. All right. So it might be tempting to call this length x, and then this little length here would just be 20 minus x. Okay. Reason why I'm not doing that is because I realize here that I've got a right angle triangle. So if I want to find, say, this is the water distance and this is the land distance, it looks like I'm going to be using Pythagoras to find an expression for the distance along the water. So the last thing I want here is a more complex expression. So what I'm going to do is I'm going to call this length here x, and so the remaining length here along the land is going to be 20 minus x. Okay, and so we already have an expression now for the distance along the land, and so now we can come up with an expression for the distance along the water. It's just going to be square root of x squared plus 5 squared. All right, just using Pythagoras. Okay, so now I'm ready to come up with an equation for the total cost here. Okay, so the cost is going to be, well, what did we say? We said it was going to be 100,000 times the distance along the water. So 100,000 times square root of x squared plus 25. All right. And then we're going to add to that the cost along land, which is just going to be 75,000 times 20 minus x. Okay, and so what we have here is we have a model in terms of one variable. All right, so we just need to find our domain for which this would be valid. So again, we said one possibility was that it goes straight down and then across. So in that case there, x would be 0. There would be no distance from this point A. So x is going to be greater than or equal to 0. Or if it goes all the way across in a diagonal, then this whole length here, x is just going to be equal to 20 because there is no portion along land. So what we have here is we have 0 less than or equal to x, less than or equal to 20. So we have a closed interval, so we know we're going to be guaranteed an absolute minimum cost. All right, so there we go. We've got our model, we've got our domain. Let's go ahead now and take the derivative. Okay, so we have c prime is equal to, so again, 100,000 is just a constant. Okay, this is going to be, we've done this many times, so 1/2 x squared plus 25 to the negative 1/2 times the derivative of x squared plus 25, which is just going to be 2x. All right, and then here we've got 75,000 is just, oops, too many zeros there. 75,000 is just a constant, and the derivative of 20 minus x is just negative 1. All right. So, of course, as usual, we want to set this to 0 to find our critical point. So here this 2 will reduce with that 2. So in the end, in the numerator, we're going to be left with 100,000 x all over the square root of x squared plus 25. Okay, and then here minus 75,000. Okay, as we usually do when we're working with this type of equation, not technically a rational equation because this is not a polynomial, but we can solve it in the same way. I'm going to multiply both sides by the lowest common denominator, which is just root x squared plus 25. So still 0 on the left-hand side. So here we're going to be left with 100,000 x minus 75,000 times root x squared plus 25. Okay, nothing we can really do here algebraically to simplify this, but we've seen this before where we can just bring everything with, bring the square root to one side and leave everything else on the other side, and then it's just a matter of squaring both sides. Okay, so 75,000 times square root of x squared plus 25 is equal to 100,000 x. Now this is where, and I probably could have done this even earlier on, I don't really want to be squaring either of these two numbers. So we see that these two numbers are both divisible by 25,000. So 75,000 divided by 25,000 is just 3. And then here, 100,000 divided by 25,000 is 4, and this is much more manageable. All right, so here now I can square both sides. Make sure you're squaring everything here. So we have 9 times x squared plus 25, because we're just squaring the square root. And then here we have 16x squared. Okay, so I'll bring the 9x squared to the other side. So 9 times 25, so that's 180 plus 45, that's 225. And then here 16 minus 9 is 7. Okay, and so here we have that x is just going to be equal to positive or negative square root of 225 over 7. And of course, we're not interested in the negative square root because x has to be greater than 0. Let's just see if this number, this critical value, is in my domain. Okay, so 225 divided by 7. Okay, and take the square root of that, and we've got about 5.7, which indeed is in my domain. Okay, so here I guess I could test signs, but here I'm working on a closed interval, so I know that my absolute minimum is going to occur either at the critical point or at one of the two endpoints. So let's test those here. So the cost at 0, so this is just going to be root 25. Okay, so let's calculate this here. So what do we have? We have 100,000 times, well, like we said, if x is equal to 0, square root of 25 is just 5, so times 5, and then plus here 20 minus 0, so 20, so plus 75,000 times 20, and that gives us 2 million. Okay, so that's $2 million. Okay, let's check C at 20, the other endpoint. See what we get. Okay. There we go. It's just a bit of a freeze on the program there. So where are we here? So we have 100,000 times the square root of 20 squared. So 20 squared plus 25. All right. And then we've got plus 75,000 times, 20 minus 20 is 0. So times 0, that just goes all together. So here we've got, well, it looks like something a bit bigger. It looks like 2,061,553. So 2,061,553. So definitely not going to be our absolute minimum. And lastly, let's check C at 5.7. All right. And see if we get something smaller than the 2 million. All right, so let's put it back into there. So 100,000 times the square root of 5.7 squared plus 25. Okay, and then plus 75,000 times 20 minus 5.7. And we get, there we go. We do get something smaller. So 1 million. So it's 1,830,722 approximately. And so the minimum cost is going to occur when this X value is 5.7. So let's see what they're actually looking for. Are they looking for the cost? Are they looking for the dimensions? So here it says what route from the well to the refinery will be cheapest. Okay, so I guess we can say, so our answer here, so we'll say along water to 5.7 kilometers from A, then along land to R. All right. So it asks to describe the route, so I'm describing the route. Okay, had they asked me to describe how long the pipeline was going to be, I would have given W and L. And if they were asking me for the actual minimum cost, I would have given this cost here. All right, so just to recap here. So step number 1 was to realize that you could have a combination of water and land, and you shouldn't assume that it was either going to, maximize the land or minimize the distance, that it could be something in between. And then from there, we incorporated our costs, and we were able to solve our problem using our calculus methods. And because we were working on a closed interval, I was able to just test the endpoints and the critical point to determine my absolute minimum. Okay, that's it for this one.